Chapter 8, Systems of Equations, Section 8.2, Systems of Linear Equations in Three Variables. We now return to the situation of Section 8.1, Systems of Linear Equations, but rather than looking at systems with two variables, we'll now consider systems with three variables, where we have at least two equations. So with two or more equations and three variables, where all of the equations in our system are linear. As with linear systems and two variables, these systems can have one solution, no solution, or infinitely many solutions. Those are the only three scenarios, just as we saw with the systems in section 8.1. Although solutions still correspond geometrically to points of intersection, here the equations represent planes in three-dimensional space. So we're talking about points of intersection of planes, flat surfaces of infinite extent, as opposed to lines. So visualizing this is a little bit harder, but it's really not necessary to be able to visualize geometrically what's happening to solve such a system of equations. We can solve them algebraically and come up with exactly the solutions that we're looking for without having any sort of visual aid to assist us. The addition, that is elimination method, is usually used to solve linear systems in three or more variables. So while it's possible to use substitution, the preferred method is addition, or what's also called elimination. And so that's the method we will use in all of our examples. So let's look at example 1. Solve the linear system. So you see three equations in three variables x, y, and z. All three of these equations are linear equations. We have x, y, and z in separate terms, x, y, and z all raised to the first power. So these are linear equations in three variables rather than two, each one of these equations representing a plane in three-dimensional space. We're going to use the addition method or elimination method to solve the system. And so the idea would be to identify a variable that we can eliminate twice by taking different pairs of equations and eliminating that particular variable. And with this system, we could choose either x, y, or z. You have more than one approach that you can take. I'm going to choose to eliminate x. That will be fairly straightforward, especially given the fact that the first equation has a coefficient of 1 for the x term. That makes it a little bit easier. So what I'm going to do, for the sake of being somewhat organized, is to label the three equations as equation 1, equation 2, and equation 3. Now, as I mentioned, the coefficient of the x term in equation 1 is a 1. So I'm going to make use of that to eliminate x in the other two equations by pairing each of those equations with equation 1. So I'm going to label this as follows. I'm going to first multiply equation 1 by negative 2. Negative 2 times equation 1. Let me write that this way. Negative 2 times equation 1. Alright, what that's going to give me is negative 2x minus 4y minus 4z equals negative 6. So I've just multiplied each term in equation 1 by negative 2. I'm going to pair that with equation 2, which does not need to be modified here. And the whole point is to eliminate the x terms from the pair of equations. So I'll do that by addition. Adding like terms, the x terms cancel. Minus 4y plus 1y is minus 3y. Minus 4z plus 1z is minus 3z, and negative 6 plus 9 is positive 3. So that gives me a linear equation in two variables, y and z. Now I can write this equation in a simpler form by dividing out a common factor of negative 3. So let me just go ahead and do that, and that'll keep things a little bit simpler for us. So that would give us y plus z equals negative 1. Now what I'm going to have to do is pair two different equations and repeat the process of eliminating x. So the simplest way to do that is to pair equation 1 with equation 3 and multiply equation 1 by negative 3. So we're going to next do negative 3 times equation 1, and that would give us negative 3x minus 6y minus 6z equals negative 9. And just pair that with equation 3, which we will not need to change. 3x plus 9y plus 5z equals 14. And then adding like terms, the x terms cancel, the y terms add to give us 3y, the z terms give us minus 1z, and negative 9 plus 14 on the right hand side is positive 5. So having eliminated the x terms from two different pairs of equations, I can now pair the resulting equations, this one and this one, together as a system of two equations in two unknowns, as we studied in section 8.1. So if I pair those two together now, the first one is y plus z equals negative 1, and the second one is 3y minus z equals 5. Notice that the z terms have opposite coefficients, so I can just directly add those two equations without modifying either one of them. And adding the y terms gives me 4y. The z terms cancel. Negative 1 plus 5 on the right hand side is 4. And now I have just one variable, which I can solve for directly. Dividing both sides by 4, I obtain y equals 1. So now we know one of the three variables. We know the y value is 1. Now we can determine the value of the other two variables. First, determining z, we can use either of the two equations we just paired together. Let's use y plus z equals negative 1. Okay, if we substitute 1 for y, and then solve for z, subtracting 1 from both sides, we obtain z equals negative 2. So that now, having found y and z, we can go back up to one of our original three equations and solve for x. Probably using equation 1 will be the simplest choice. So from equation 1 we have x plus 2y plus 2z equals 3. I'll just recopy the equation. Then I know that x is still unknown, y we determined to be equal to 1, and z we determined to be equal to negative 2. So if we look at what we have on the left hand side, we have x plus 2 minus 4. That's going to be x minus 2. x minus 2 equals 3, and adding 2 to both sides, we would obtain x equals 5. So let me just write the solution up above here, since I'm kind of out of space. What we have found is that this particular system has just one solution. We would classify this as a consistent system with just one solution. And that solution would be an ordered, what we call an ordered triple, x, y, z, where x is 5, y is 1, and z is negative 2. So write it as an ordered triple. X is 5, y is 1, and z is negative 2. We'll continue with example 2 in the next video.